Scientific notation. And again, scientific, it says the word science. This is often used in science for really big and really small numbers. Like, again, millions, billions, 20 billion. And here we got, what, tenths, hundreds, thousands, 100,000s, 10,000s, 100,000s, millions. I got 51 millionths there. Both big and small numbers. The biggest thing we have to put our arms around is both those numbers, but we'll talk about the larger one, is it's one term. Alright? 20 trillion is one thing. And when we're done, it's still one thing, except we're going to break it into factors. And it's still one product. And the thing is, you got to see equivalency. 2 times, and then I listed the tens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I wrote the 10 tenths. That is still equivalent to 20 trillion. And I can write the 10 tens as 10 to the 10th, the base number of times. And it's still one term. So when we're doing scientific notation, we have to realize it's always equivalency. It's just operations. It's not special. It's not different. The only thing about scientific notations, it's always in this format right here. Some number n times 10 to the a power, where a is an integer, -2, -1, 0, 1, 2, 3, 4, just those type of numbers. And n is either equal to 1 or less than 10. It is this conjunction. And again, it's just a nice way to notate it. It's just a rule we use. So if I have 2,100,000, I can write it as 21 times 5 tens, but 21 is not between 1 and 10. Well, to do that, I have to make it into 2.1. So I do, that's just the 21 I'm looking at. I say 21 divided by 10 times 10. This is equivalent. I multiply the top and bottom by 10. When I take 21 divided by 10, I get 2.1. And when I list the 10 here, I get another 10. So now I have 10 to the 6th power. Often when people look at these, they count 1, 2, 3, 4, 5, 6 places, and they place a decimal place in 10 to the 6th. And that's a nice shortcut, but it's important we understand how we're getting there. How 2.1 million is equivalent to 2.1 times 10 to the 6th. 2,100,000. How these are the same. If you check it's the same, you'll never make a mistake. So again, I have 47,800, which I can write as 1, 2, 3, 4, 4 times 10 to the 4th. 4.78 times 10 to the 4th. And over here I have 3,020,000. 1, 2, 3, 4, 5, 6. 3.0 times 10 to the 6th. And again, I show the steps here. For the first one, 478 times 10 times 10. Then I divide by 2 tens to make it 4.78, and I put 2 tens up, 10 to the 4th. Over here, I'd make it 302 over 1 times 10 times 10 times 10 times 10. And I write 302 divided by 10 by 10. And again, it's really important for us to realize that if I want to count decimal places, it will work. But where students get confused is, do I have a positive, negative power? If you write it out this way, you'll always see what it is. Because the other option is like this for really small numbers. 0.003. How do we write that scientifically? Well, I start that we have 0.003 over 1. And I need this to be between 1 and 10. Well, to do that, I say, hey, I got to move the decimal place 3 places. So I multiply 10 to the 3rd on the top, and then I have to multiply by 10 to the 3rd on the bottom. So I take 0.003 times 10 times 10 times 10 on the top over 10 times 10 times 10 on the bottom. And I get 3 over 10 to the 3rd. When I bring 10 to the 3rd from the denominator to the numerator, I have to change the exponent sign. 3 times 10 to the -3. And again, people count. And that does work. But again, you have to understand why it works to make sure you don't make sign mistakes. Likewise, over here on, let's see, tenths, hundreds, thousands, 10,000, 4,200 thousandths, I multiply by 10 to the 4th. And I get 0.00042 times 10 times 10 times 10 times 10 divided by 10 to the 4th, which makes 4.2, which then you bring it up, becomes 4.2 times 10 to the negative 4th. It's important to slow down and not guess at the sign. You notice I'm not using any rule statements like left, right, positive, negative. I don't like those rules. They do exist. I think we can take a look here at 4 more examples, and then I have 2 more to end with. We can also mix it just for practice. Usually you wouldn't write a number this way. So like 32,000 times 10 to the 7th. One product. One term. I deal with the 32,000 separate of the 10 to the 7th. 1, 2, 3, 4. I know that I'm going to have to divide by 10 to the 4th, so I multiply. So I get 3.2 times 10 to the 4th times 10 to the 7th. Same base, so 4 plus 7. 3.2 times 10 to the 11th. Moving to quadrant 2. 47,300 times 10 to the negative 11th. Again, 4.73 times 10 to the 4th. I made a math mistake all the way through on those. 4 minus 11 makes 4.73 times 10 to the negative 7. Next one, 0.003 times 10 to the negative 7. Alright, I have to make that into 3 times 10 to the negative 3, which I show through here, which gives you 3 times 10 to the negative 10. And again, I show the steps right here to make it work. On the last one, 0.0042 times 10 to the 7th. Now, here's a case again where I make 4.2 over 10 to the 3rd to convert this to the equivalency. Well, I use the quotient rule, 7 minus 3 leaves me 4.2 times 10 to the 4th. I got 3 examples to end with. I said 2, I meant 3. Alright, the first one, let's see if I can do this right. 1, 2, 3, 4. I realize I'm multiplying by 10s here to make it bigger. So I'll write it as 4.99 times 10 to the 4th. Now, you'll notice I use the same number. So this is 4.99 times 10 to the 4th times 10 to the negative 11th. One product still. Bases are the same, so I add the exponents. 4.99 times 10 to the negative 7. And then finally, I have a number here. I know I'm going to have to multiply the top to make 4.99, but I'll have to divide by it. And again, I really like to write it out. 1, 2, 3, 4, 5. So that's over 10 to the 5th. That's the equivalencies. 2 minus 5, 4.99 times 10 to the negative 3rd. The number one thing about scientific notation is realizing it's just factors and products. It's a rule, but it is not special. You can always do the math and check your answer.